So we're going to talk about system of equations with three variables. That's what this section's titled. And you'll notice that we're kind of jumping into 4.4. We will review previous learned material. And you might say, well, I forgot how to do that. Don't worry about it too much. We're going to go over it. This is a big field. And there are several different ways to solve systems of equations. I can think of like 4 off the top of my head. But we're not going to do all those. We're just going to focus on the elimination method. And so we'll go through that and show you how to do it. These problems are a little long. They take a little bit of paper, a little bit of organization, but they're way fun. and we're just doing it in this one section. So normally we kind of build on mathematics, but this is a case where we're kind of just inserting this section in here. Okay, so back a little bit of a review. So systems of equations with two variables, you might have something like, 2x plus 3y equals 6. And then you might have something else that says x minus y equals 8 or something like that. That's called a system of equations. And what happens is they're both linear equations, and you can graph them in a Cartesian coordinate system. So you might graph them, and you might have one line that graphs like this, and another line that graphs like this. And then the solution is where those two intersect, okay? So now this is a system, I'm talking about a system of equations with two variables, and I'm just doing this as a little bit of review or knowledge, and so that we can spring into the next part. Okay, you might have a system of equations. It's easier to explain it with two variables, so then when we go to 3, hopefully it'll make a little more sense. So you might have a system of equations and you graph them, and one line graphs like this, and another line graphs like this. And these would be called parallel lines. Tried to draw them parallel. And there would be no solution in this case. So over here you have one solution, and the point is where they intersect. That's the solution. It's an ordered pair, whatever the x and the y are. I'm putting x1 sub x sub 1, y sub 1 just to indicate that point there where they intersect, okay? So those are two cases. We call the second system inconsistent, okay? So let me write that up here. This is inconsistent. Because you're trying to get points that would work for both lines, and that's not going to happen. Okay, the third case is kind of an awkward case, in my opinion. But it happens. So you might graph a line like this, and then when you go to graph the second line, it happens to be the very same line. And so they're right on top of each other. And so in this case, by the way, all these lines should have little arrows on them. I just am lazy, but now I put them all in. Okay, so this is called a dependent system. Dependent system. And you don't really have a system of well, they gave you two equations, but they wound up being the same line. And so there are an infinite number of solutions. Infinite number of solutions. And the solutions are all the points that are on that line. And so there are all these little points along this line. There's an infinite number of them, and all of those points satisfy both equations, so they're all solutions, okay? So that's just a little bit of the terminology, a little bit of like what happens when you have two variables. Okay, so now we're going to go into three variables. And I have a bunch of pictures here. These pictures are also in your textbook, so they might be easier to see that way. They're really hard to draw, so I didn't draw them. Okay, so here you have the first case. And a system of equations with three variables, you're going to see them because we're going to solve them, but you might have something like x plus 2y minus z equals 10, and then you might have x minus 2y plus 3z equals 15, and you might have negative x plus y minus z equals 27 or something like that. Anyway, that's just an example. I'm just making stuff up. But that would be a system of equations, and you'll notice you have three variables in here, x, y, and z. Now, they can use other variables, but traditionally we just use x, y, and z. And so to graph these, you have to graph them not in a Cartesian coordinate system that's a plane, but you have to go three-dimensional. That's why these are so hard to draw. So this first case here where I have this arrow, the planes are intersecting at supposedly one point. That's where they all share a common point. And that would be one solution to your system of equations. And you're going to write that solution as an ordered triple. So x sub 1, whatever it is, y sub 1, comma, z sub 1. That would be the solution. You're getting one solution in that case. Okay? So each plane is representing an equation. So when we graphed equations with two variables, we graph a line. But in three variables, it's a plane, meaning like a piece of paper. Okay? So another case you could have is maybe the three planes are like parallel. Maybe there's no points of intersection. They don't share any points in common. And so in this case, there would be no solution. So you can write no solution. I think WebAssign likes that, or you could use the empty set as well. Okay, now this third case says two of the planes are coincident. That's what they call that case where the lines are the same. They call it coincident. I forgot the word. So let me write it up here because I'm sure you can't see it. Coincident, meaning it's the same, in this case, plane. So it's like you've got a sheet of paper, one plane, and then the other two are actually the same sheet of paper. And so you have no points of intersection. There's no solution here. So no solution. In another case, you have two planes that are parallel. So in this case, those planes are parallel. And they intersect at the third plane, but they don't have any points in common. So there's no points that are both on the red, the dark blue, and the light blue. So again, there's no solution. And they're just kind of pointing out to you these different cases. You really don't have to worry about them too much, but as far as understanding visually what's going on. Okay, so here's a third case. You kind of get the planes, you know, the red and dark blue intersect down here. The red and light blue are intersecting there, and the blue and the light blue and dark blue are intersecting there. But none of them have any points on all three planes, so there's no solution. Okay, now in this case, this third case, you've got all three planes intersecting. They're sharing a line here, okay? So there's going to be infinitely many solutions. Infinitely. Pretend that says infinitely. Many solutions. And the solutions are all going to be that line. But we're not going to worry about that. We're just going to put infinitely many solutions. And then finally, you've got two planes that are coincident. Okay, so same plane as the other one. And they intersect that red plane. And so again, there's infinitely many solutions in this case. Okay, well, infinitely many solutions. Now, don't worry about the pictures too much. You don't have to draw them. We're just trying to give you a visual of what we're talking about as far as these systems go. So it's information, hopefully, oh, forgot the last one. So all three planes are coincident. It's all three planes were the same. So all three the same. Same plane. And so you get an infinitely many solutions. Now, like I said, we're not going to draw these out. We're going to show you how to algebraically work with them, okay? And I think that's all I have for this one because it's kind of a long video. All right, so stay tuned to the next video.